So howdy, we are Team Stabilicore, and this is our final presentation. And just as a disclaimer, we are all in the same space, but we're wearing our masks, so we are COVID safe. So I'll go ahead and begin with our introductions. And so just to go over what we're going to be overviewing today, just the background of our project, along with, of course, all the electronic and software and mechanical aspects of the project, as well as some diagrams that we have put together, and then the project status and financials of the entire project, and then finishing off with our conclusion. So to start, I'll go ahead and introduce myself. So my name is Macy McClooney, and I am the project manager.
Howdy, I'm Nathaniel Blevins, and I'm the software engineer for this project.
Howdy, I'm Shrutan Sharayat, and I'm the hardware engineer for this project.
Howdy, I'm Liz Sanchez. I'm the integrations engineer for our project.
And so Dr. Kim, of course, has been our sponsor and advisor. And for those who will be watching this video and may not know, her previous research experience involves modeling the nervous system and human behaviors. So it ties directly into what our project is related to. So currently, the products that are on the market that are similar to ours are rather bulky and can get expensive as well. So these are balance boards that can repair damaged nerve endings caused by just different injuries and things like that. So these patients are needing physical therapy to be able to regain their balance and restore those damaged nerve endings. And so, like I mentioned, these existing products are more expensive, can also get very bulky as seen in the image on the left. And then non-mechanical ones require somebody else to be standing there to make sure to hold them up per se. And so the help of handlebars will assist with this. And so what we are delivering with our mechanical balance board is providing a physical therapy plan for our patients, as well as being able to control the angles that are moving with the motor, and then collecting data from this with the use of the sensor mat and different angles that we will be collecting, and then completing within our budget of $5,000. Okay.
So this slide for the beginning of our deliverables shows our previous designs and what we had kind of gone through to get where we are now. The beginning of the semester, we started with a linear actuator design that you can see on the left. It would have utilized 4 points on each end to help us move the board. We realized that that was going to be too slow. So we then moved over to just motor design, which we have on the right. They use 2 motors connected on opposite ends. And we kind of realized that that design wouldn't quite fit what we needed. And so eventually we got to the 1 motor design that we came to now in our conceptual block diagram. Here kind of shows the idea behind that. It's going to be an actuating motor-driven board, up to 25 degrees of tilt, has a 350-pound weight limit, it's pressure sensing, and comes with a desktop application to help control those angles.
So moving on to the functional block diagrams, this is an image of the electronic components that we're using. So we're using 2 12-volt batteries in series with each other to create a 24-volt charge that we drive directly into the motor driver. The motor driver then in turn powers the 24-volt 350-watt motor. It's controlled by the ESP, and there's a connection between the ESP and the motor driver itself. And the 74HC4051AP is MUX-DMUX combo that we're using as a buffer between the ESP and the motor driver to control the current that's being fed to the motor driver to control the speed of it. We're also using 6 other multiplexer, demultiplexer combos for the sensor mat that we created ourselves. We're using 4 SN74HC4851 and MUX-DMUX combos for the rows, and 2 of those same chips for the columns. So for on the rows, we have 16 rows on the sensor mat itself, and we have 8 columns on 8 columns on one of the sensor mats, and we have 2 of these identical sensor mats located on each side of the board to accurately read both feet. And we're also using the LSM9DS1 as our to measure the angles that the board will be reaching. So moving on to the sensor map diagram. So the way that this works is with the 8 columns and 16 rows, we're creating 128 data points that we can read the 1 foot with, and it's similar on both sides. So on the rows, we're cascading 2 of the SN74HC 4851N muxes to read the 16 rows of data, and we're using 2 per footpad for the rows, and for the columns we're just using 1 of those chips since it's an 8-to-1 chip. And on the column side, we're using 8 1K pull-up resistors to avoid saturation. The electronics that we're going to be using for this thing is the microcontroller is the ESP32. The sensors that we're using to gather the angle is the LSM9DS1. The motor driver that we use is the L-Faster 24 volt, 36 volt, and so it comes in a variable voltage and power wattage range, and it's a brushless motor controller. The sensor mat we created ourselves with copper tape and Velostat. The motor is a 24 volt, 350 watt motor, and we're using 2 sets of multiplexers. The SN74HC 4851Ns as the 8-to-1 16 AIPs, and the other is the 74HC 4051AP 8x1 16 AIPs.
So moving on into kind of the software side, I'm just going to give you all a little electronic overview of some of the technologies that we've incorporated into our design. So on the software side, we are using Python to code all of the GUI implementations, and some of the modules that we're using that kind of haven't been taught to our program, but I was kind of familiar with, but still needed to brush up on to complete this project, were PySerial for the Bluetooth communication between the desktop application and the ESP that we're using as our microcontroller. Multiprocessing, which I was able to use more CPU on my computer in order to speed up the GUI delays in order to minimize them and just make the program run faster. And the multiple programs that I'm using in that is one to communicate with the ESP and the other one to display the GUI. So tkinter is our main source to display the GUI. It's an object-oriented library that offers many objects for visualization of whatever controls you want to display. And then matplotlib is used to display the heat map of the sensor pressure pad that you can see in the GIF on the right. And then XLXWriter is used to create the data that we are exporting at the conclusion of the program. So as far as the microcontroller, we are programming with Arduino on the ESP. And the only 2 modules that we use for that are serial Bluetooth in order to connect with the PySerial on the GUI side, and the SparkFun support module, which is used to control the LSM in order to predict the angles. On the hardware side, I just want to talk about the sensor mat implementation that we did a little bit. So we actually found some open source projects that use Velostat and copper to make a sort of sensor mat. The first one that we used was the Velostat pad, which was found on an Instructable website, which was basically just a Boolean indicator that says that you're standing on it or you aren't. This was kind of helpful for us to kind of introduce ourselves to how we could implement this similar thing instead of buying a expensive, already on the market type. The next was an OMAT Velostat trackpad, which was very similar to what we're using in this, but with less resolution. I believe it was just an 8x8. And it wasn't using multiplexers, it was using kind of a clock-based component, a shift register. And then the last one was the Hackaday body size pressure sensor map, which Dr. Kim directed us toward to reference. And they were also using shift registers at a much larger scale. And we are actually able to get a more resolution in a smaller area than they were able to over the course, but I'm sure that their project requirements were satisfied with their resolution. So moving on to the software flowcharts, the first one that we did was kind of an overview of what is happening on the ESP. So whenever it connects to the Bluetooth device, it essentially just checks to see if it's receiving a message, and if it's not receiving the message send, then it means that it's received an angle, and it PIDs to the angle, and then it starts to send the position and pressure data. If it doesn't receive the angle, then it just sends it, so that whenever you're in coast mode, it constantly sends position and pressure so that you can view it on the GUI. And the PID that we are using is actually just a proportion derivative controller that we use to stop the motor whenever it reaches the desired angle. The integration gain wasn't included because we don't want any overshoot to make the angle as accurate as possible for physical therapy applications. So this is a closer look at our PID controller. It's just a basic grab the time on a continuous loop while it hasn't reached the correct angle. And then it calculates the rates and then calculates the output and exports it to the motor driver. It puts the PID on the pin that goes to the throttle of our motor driver, which is used for electronic scooters that controls the motor. As far as position data, some of our older designs were capturing the pitch and the roll, and we have consolidated this to just the pitch to save that tiny bit of time to increase sampling speeds. Plus, pitch is the only one that we're really concerned with, and it basically just finds the pitch using the accelerometer data, converts it into degrees instead of radians, and then does an error check to make sure that the absolute value of the pitch is less than 25. If it's any greater, then that means that there's a little bit of noise in it, and so it just restarts, and once it finds a good value, it exports it back so that it can be sent to the GUI. Looking on to the pressure side, as Shruthan mentioned, we're using two 8x16 sensor mats that are designed with 16 rows that force voltage one at a time, and then whenever a row has voltage forced to it, the columns read the ADC value one at a time in order to get 128 points of data, which can then be stored in a matrix and then exported to the ESP. Some of the methods that we use to kind of save on pin space and efficiency was all of the select lines for both pressure mats could essentially be the same. The read in pin for each of the pads needed to be different just because they're reading at the same time. But also the output of the rows could be connected straight to VCC instead of actually forcing a voltage because it was already getting 5 volts. And so all of these kind of reduced pin space so that we could use the smallest ESP that could get the job done. As Shruthan said, we cascaded multiplexers to double the resolution, and this was done just through using the inhibit pin, pretty simple. And then pull-up resistors were implemented on each of the columns that we receive the ADC value on in order to avoid saturation. In addition, we put some implementation on the visualization code so that it auto scales, so there's no saturation on there. And then both mats read concurrently instead of reading one at a time, which reduces the sampling rate, or increases the sampling rate, I should say. So moving on to the GUI, we start with the main loading screen. A lot of the GUI pages are either for aesthetic or organization until we get to the main program. So starting with the main load screen, it's just we're able to select a user profile that has been used before. This is for returning patients, or we can create a new user. And there is an error check on this screen to make sure that a user's profile has been loaded up and is valid before you can actually connect to Bluetooth to avoid any crashes that could occur later on in the program. So moving on to load user profile, basically we came up with a list of some relevant information that physicians or researchers would need on the patient that's going to be on the board. And so some of this included username, age, height, weight, and any notes that could be referenced by continuing physicians if the physician's changed between patient uses. And all of these are stored in a text file that's stored in the user's directory. So the user gets its own file, and all of their therapy sessions or uses get stored in that file to keep everything organized. Once the user is done here, it goes straight to the Connect Bluetooth screen, or if you loaded a previous user's profile, it'll go straight to the Connect Bluetooth screen, where it'll look for connectable devices in the area, display all of the device names and MAC address. Ours happens to be Stabilicore Balance Board to make it easy. And then once you find your device, you click it, and then you connect Bluetooth, and it exports to the main page. And there's an error check here too to make sure that you have selected a value or a device before it moves on to the main loading screen. So now we get to the main loading screen, which is where all of the functionality happens. So whenever you get to the main loading screen, it connects to the ESP. It displays the current pressure sense on the top, and then it displays the notes and the name of the user on the bottom, as well as an updating angle of where the board currently is. We have the option to either edit the user, in which case you can edit any values you want and resave the file. You can load a custom program, which we have outlined how to do that in our user's manual. And basically it's just a list of angles for a specialized therapy session. We do have preset programs available for anyone who might be coming for the first time and just needs to get a baseline reading of how they're doing. And then the stop button, which stops the program, saves the file, and breaks the connection with the ESP. So as I mentioned earlier, we are using multiprocessing to kind of speed things along with the GUI. And in that, we're just sending the command to the board. We're receiving pitch data, sending pressure data, and then putting it on the queue, which is read in from the main GUI and put into their corresponding objects using the tkinter software.
So for our mechanical overview, this is our board as a 3D model. The only thing this doesn't show is the brackets that connect us to the tire, as that's what is used to show the connection. That is what connects the board to the actual movement of the motor. So we use a single DC motor as a one-wheel inspired design. We need to move 350 pounds from level and force that user to tilt around. That meant that we were moving about 158 kilograms. We used the equation of torque is equal to our radius, which is just the distance between the distance from the center of rotation to where the weight is, times the force times the sine of theta. Sine of theta was 1 here, as the center as our center of mass was focused right above the wheel. Our radius was about 6 inches, or 0.1524 meters, and then our force was about 1,470 newtons. And so the torque needed was about 165 foot-pounds. We did find that was a little bit lower during testing, mostly because that would require you to be perfectly balanced on the board. And generally, whenever we were trying to balance on it, it was a little difficult to keep perfectly balanced. So this was the peak. And then the supports used to hold the platform were meant to allow the motor to turn, allow the hub motor to turn without allowing the shaft to turn. We had issues with this earlier, and issues again with it recently, where the weight from the user would apply too much force to the shaft through the motor and would force the motor shaft to strip our supports.
So now we're going to go ahead and move on to the demonstration of the board. What we're going to be doing is Nate's going to show the GUI interface, and Elias is going to join in on his phone and take a video of the board actually working. So Nate,
I think that the best way to actually view this with the GUI and the demonstration running at the same time is if you do the split screen to the speaker view and then pin Elias's video on the second half of the screen so that it can show both at the same time. They can pin this one. So I'm going to stop sharing. Oh, I'm going to exit the PowerPoint. Which, there we go. So, and let us know if you need help, like with viewing Elias's video and the desktop application at the same time.
You might want to, whoever's in charge of the meeting might want to pin Elias's view.
I think it's done on the on y'all's side. If y'all click the 3 dots on the top right of his camera, I think it has a pinned video.
Okay, yeah, that works.
Okay. Excellent. Y'all can still see my screen.
Yeah.
Okay.
Yes.
So here's the main screen of our desktop GUI. So as I said before, we have the option of loading a user interface from any directory on your computer, or you can create a new user. And you can't connect to the board unless a pathway has been indicated as to the user file. So we're going to go ahead and create a new user called example. The age, we'll just put 21. Whoop. The height, we'll do an arbitrary value 5'11". For the weight, we'll put 150. And then notes, this is an example. So then whenever we add a new user, it goes to indicate where you want to save the file. So I have a Stabilicore patient records file that I will select, and it saves the user into, along with its information in that area. And so if I go back and just kind of look for it, I can see that we have it right here. So you can do either way. And then it goes straight to the Connect Bluetooth screen. We won't be finding any devices because the board's not on. So Shruthan will turn it on with a switch located on the bottom of the board. And then Elias will go ahead and give y'all a rundown of all the positions on the board while I get it connected.
All right. So down here, the battery connections are up front. That allows access to the batteries to let them charge. We also have our sensor mat board up here. Right now, the sensor mats are covered with electrical tape for us to be able to stand on it without damaging or pulling on the copper tape and Bellistat. And then farther below, we have our electronics. They are a mess right now, mostly because we had to make the entire structure again in the past few days, as the motor, through a lot of testing, stripped the supports that we had previously had. We tried to make some more durable metal supports using the same design or the same layout for these wooden legs. But ultimately, that stronger support stripped as well, and so we had to go about getting a new support that is welded to our axle, and that meant that the width of these two wooden legs had to be wider than we had originally expected. So the whole internals had to be taken out, and then we did a bunch of testing, and eventually they were put back in just in the past day or so. The wooden boards on the outside were not able to be painted, unlike everything else, because we had to cut those within the past day. We have foam here to allow the board to close completely without crushing any of the wires down below. And then our handlebar here allows for the user to hold on while they're on the board.
So as you can see from my screen, I have successfully connected to the board. It takes a couple of tries, so you have to be relatively close, but it does connect. And as you can see, it shows the sensor mat in the top. And you will notice that there's a little bit of noise coming from the top and bottom. That's just from some pressure on the edges of the board where we have our covering. And since it auto scales, it just gets accentuated whenever that's the highest amount of pressure on the board. So Shruthan, if you'll go ahead and step on so that we can see what it looks like with pressure. So as you can see it quickly changes and updates in real time, and the board angle can be displayed on the bottom. So this kind of shows where Shruthan's putting a majority of his pressure. So right now it looks like it's on his left foot and on the right side of his right foot. So the command list of angles that the board can go to can be seen on the left. And as I mentioned before, we have some preset programs, which is basically a text file that is located within the directory of the program. So with full range, it's kind of a baseline of every value that the board can reach. And then if you want to load your own custom program, you can go ahead and select it from anywhere on your computer. So I'm going to go into custom program where I have created a test function. So to kind of go over the error checking that happens on the GUI on this phase, if you put in a value that's not an actual integer, then you get a error on the screen that kind of indicates how you should fix it or why nothing is happening on the balance board. If you do a value that is too high, like 28, or too low, like -92, then you get an invalid angle error. And that just kind of tells you that maybe you should reference the user manual that indicates what values are acceptable. And these values won't be sent to the ESP at all, so that it stays outside of the range of error. So we're going to go back to the full range value. And if you look at Elias's video, we will start sending an angle. So first angle we're going to go to is -15. And it just quickly goes to it. And once it reaches the angle, it goes into coast mode and kind of tests his recovery. As you will have noticed, it does move rather quickly to knock somebody who even has pretty okay stability off balance. And the handlebar is positioned in a way that he can easily grab onto it if he feels like he's about to fall off. That's for patients with maybe a little bit less stability. So moving on to another angle, maybe on the other side of 16. So whenever we hit the reverse pin, just from the way that we had to reverse engineer how to reverse the motor through the motor driver, it does take a little while to hit the reverse, but all this happens in whenever you're first sending the angle, and that's just because there's no overshoot, so it doesn't have to reverse in the middle of going to an angle. So if I do want to edit the user, as I'll show you, you can just click edit user, all the information comes up. And then if you want to stop or edit the information here, you can edit here too. So if I decide to stop the program, then we have a save test box that comes up that has the current date and the time so that it keeps everything organized, and it loads back into the profile that you created right here. And if you save it, I can go ahead and open it up under example. And what will load is three columns. One of them has the current time down to the microsecond. I'll let it open up real quick. The second column will show the angle that it was taken at. And then the third will be the live representation of the sensor pad at the time. So once it opens up, it generates pretty big files because we're implementing actual like PNGs into the design. But if I do scroll down, you can see it tracks it in real time. And it only tracks in coast mode, so it kind of gets rid of irrelevant data that's during the motion of the PID, because obviously the user will be off balance there. And yeah, these files are stored so that you can reference them at any time. And once you create a new file, as long as it's not in the same minute, then it will go ahead and save as a new file. So I'll go ahead and go back to the presentation now.
So for the project status, the accomplishments that we feel that we have gotten to are that the motor control program is able to actuate to angles in 2 directions. The desktop application is able to wirelessly communicate with ESP through Bluetooth and display the board's current pitch and roll with a latency of about 150 milliseconds. The board is structurally complete and tested.
So to cover our Gantt chart, this is a high level look at our Gantt chart. So without the collapsible task expanded. So you can see that it goes from the start of the semester to when grades are due. And the red line indicates today. And the key points of this one is the alpha design, the beta design, and the final design. And I'll go ahead and go to the next slide where you can see our low level of our alpha design. So this was, of course, in the beginning parts of the semester where we were doing a lot of research for the sensor mat and the motor and things like that. And then alpha software as well, where Nate was doing some things with testing the microcontroller. And some of this had to be adjusted at some points, but ultimately we met our goals for scheduling for alpha testing. And then for the beta design, similarly, we have just the software hardware layout here. Different things required different amount of time. So constructing the board, as you can see, they're closer to the middle of the screen, took a little bit more time. But yeah, ultimately we reached our goals for the Gantt chart. And so going into the user manual, this was important for us because we know that to explain these kind of things in a easy to understand way, for an everyday person to use the board, this was necessary. So it's about 8 pages long that has health and safety information, as I've put a screenshot on the screen in front of you that shows, how to be alert when using the board, making sure that you are with your healthcare physician and that you are either barefoot or wearing socks that ensure that you're not going to slip off. And as well as it has the product description, it has contact information, things like that, and then images to show exactly where to go on the board for certain things or how to use the GUI as well. It has screenshots of that within the user's manual.
So a lot of the problems that we encountered had to deal with the available support that we could find. There's very little support for the motor that we had, and especially in getting it to change speed and direction. We had very little documentation that actually came with the motor driver. And like Nate mentioned earlier, we used a bit of black box sort of engineering to basically discover that the reset pin needed to be manipulated to actually get the motor to go in reverse. We had unreliable support for the sensor mat that we were trying to create. We had mentioned earlier that a lot of the sort of references that we had tried to use were projects that either weren't too applicable to what we were doing and needed to be modified, or just the code didn't work whenever we attempted to use some of it. So we had to research was needed to generate our desktop application, as a lot of that information we had never really used when dealing with sort of the Bluetooth Classic connection instead of BTE. And then wireless communication between Python and Arduino was required. So doing research on the serial libraries and how to communicate between those two were all issues that we had to deal with.
So to switch gears into our contribution slides, so I'll start with myself in what I've contributed to the project as project manager. So I was in charge of creating and keeping the Gantt chart updated, as you saw previously in our weekly TAP meetings. I had to update that and make sure that we were staying on schedule. Of course, with COVID or the snow week that we had, things did get off track sometimes, but ultimately we were able to pull together at the end and finish it on time. And then also creating and updating the website that we have, which we have outlined in the user's manual for people who want to see the progress of the board and things like that. Creating slides for team meetings, TAP meetings, demonstrations, things like that. putting those together for the team, and in the beginning stages of the board, just completing research on the one-wheel design, as well as sensor mat materials and things like that. And then the 3D model that you saw in the presentation is what I had put together in Inventor. And then, of course, communicating with Dr. Kim or anybody else that was related to the project, and making sure that we were communicating professionally through email. And then creating the user's manual for the board. I had put that together with all the different screenshots and making sure that all the health and safety information was in there. And I also used this in comparison to other similar items that are in the market already, and making sure that we hit all the key points. And then lastly, just working on the final documentation of our report. And then the cumulative hours for myself was 351.
So as far as my contributions, I was mainly in charge of creating the pressure sensor mats, all iterations of it. So we had 3 iterations, and the 3rd iteration being the final sensor mat itself. I also helped to find and order all the necessary parts. I worked with Nate to find all the electronic components that he needed in order for his software to work on the board itself. I was in charge of creating the all-team schematic, which, since we actually didn't end up using PCB design, we actually just used it as a wiring diagram for the proto boards for the final demo unit. I also helped with the physical construction and assembly of the boards. I cut all the wood, all the metal supports, all the sanding down, all the painting, mounting, and I helped with some wiring as well. And also I helped with troubleshooting in testing phases when we were testing for the past week or so, and my cumulative hours came out to about 392.
So as far as my contribution to the project, as you will probably have noticed, there are quite a few software components to this, whether it be the PID controller or the sensor mat, or even finding the angle. We did need a lot of different components for just the onboard alone, in addition to the entire user graphic interface. So my contribution mainly included designing and coding the graphic user interface to connect to the ESP, working on the PID controller, which took a couple weeks to fine tune with test motors and the actual motor. The accelerometer to get accurate angle readings with minimal noise. The noise issue did come into play with the PID controller, because if it got a really high value, then it would completely mess up the movement of the motor. And then moving on into the sensor mat phase, just finding belostat support that was reliable or helpful in writing my own program, which I did end up doing. And then visualizing the 8x16 sensor mats and exporting that data as quickly as possible, and making sure that sampling rates stayed in an acceptable value. And then I offered support to hardware and integration in implementing the sensors on the balance board and creating the proto board so that everything was wired correctly and could communicate with the ESP effectively. So cumulatively, I worked about 424 hours on this project.
Sorry. So for my contribution, I set the layout for the proto boards that we ended up using in our final design, and helped find and order all the necessary parts that we needed for the board. I soldered all the final connections. I helped with physical construction of the balance board, from cutting it to mounting it, and then eventually wiring it. And then I helped troubleshoot while testing and assisted while coding, trying to fit that role in between hardware and software, and mostly deal with a lot of the electronics. And so that meant that my cumulative hours came out to 373.
So as far as our overall labor status, we estimated in 419 that we would do about, it would take about 900 hours to complete this project. In 420, we had to recalculate that to about 1,300 hours. And our total labor ended up being 1,530 hours. And we took about 15 weeks to do it, with about a minimum of about 102 hours. The reason that we overshot our estimate was because of these last few days, as Elias mentioned earlier, the supports themselves kind of came undone. So we had to, find the right material and everything and recut it, resand it, remount everything, and take out all the components, rewire. And that's the only issue that we really ran into towards the end of this project, which overshot our 420 labor estimate. As far as financial status is concerned, originally in our SDP, we calculated it would take about $1,400 to complete this project. The main expense of that being, we were originally going to procure sensor mats through a company called Catronics and use their sensor mat and their controller for the sensor mat, and that came out to about $920. But when we started 420, we had decided at that point, it was like, it's not worth it to go through all the trouble of getting that. So we figured it would be better and cheaper for us to manufacture it ourselves. And it came out to a similar quality of the sensor mat that we were going to procure. All in all, our cumulative costs came out to about $537. This does not include shipping. Shipping came out to another, I think close to $250 or $300.
Okay, so to wrap up our presentation, I will cover the deliverables for our project. So ultimately, we've produced our mechanical balance board as planned. We have our user interface application and the user's guide to make sure that people know how to use our board, as well as the viewable data for a therapy plan, viewing the sensor mat data and also the angles and making that sort of comparison. And then lastly, just completing within the $5,000 budget, very much below, and then within the given timeline. So thank you for listening and for your attention. And we can take any questions or comments now. And yeah, thank you.
Very
All right,
good.
Dr. Kim, I'll let you get started.
Sure. I really like the actual outcome, and I really appreciate, like, we had the change of the design, the only of the 420, but it actually went out well, and I'm very satisfied the design. Well, I think the one wheel design goes to the one direction of the movement. Well, one direction, but I think it's still very meaningful. We had a preliminary data using non-motorized 1D balance board, one directional balance board, and we are hoping we can give the electrical stimulation to have the rehab study. So I'm very hopeful we can extend this to the further study. One, maybe the data saving you actually saved as the PNG, if I remember. Can we also do any like number-based column?
Yes.
Yeah. Okay.
As well. I just thought that it would be easier to view it as data, so that.
Well, sure. I think that's still good. Also, maybe for further analysis, it might be also useful. We can have the saved file as a number, then we can actually get the where is the center of mass and how we can actually get the balance between the two foods. So I think that if we can simply change the format of the data saving, I think that's also good. And the current like electronics on the side, are you going to plan to have the casing or simplifying the wiring or so?
So we have
Right now, we do have some covers that we cut for the old supports.
Right. Okay.
Yeah, we have some covers that we cut for the old supports, but we did not have time to cut covers for the
Yeah, sure.
they're a little bit different
Right.
size.
I see.
So
I see.
are you going to do that though for final delivery?
Yes.
Yes,
Yeah,
we can.
Okay, that's good. Yeah, because well, we don't really have the PCB and the protoboard. I think is worked out pretty well, but just only the concern is the currently wiring or the securing the board seems to be need to. Well, you had the idea of that, but we couldn't really make it until today. So maybe that would be nice. How you can secure it and simplifying all the wires, or maybe labeling would be helpful for future study.
We can get that done.
All right. Otherwise, I think, well, the noise for the med, maybe we can do some post signal processing, but also that we can consider that for future. But I think in considering the low cost sensor mode, I think it's still very good, and the speed, the sampling rate is still very promising rate. So I'm very satisfied with the improved sampling rate, and also the higher number of the data point. We had it 8x8 before, but now we have a very good visual representation as well. So I'm very satisfied
Thank
with
you.
the performance.
Thank you.
Yep, I think that's all from my
Okay,
side.
so I've got several questions. The first one is, I don't know if you guys have been watching the news here in the last month or so, but are you familiar with the Peloton recall that just occurred?
I've not read anything about that.
No.
So it occurs to me, so the Peloton issue, it's a treadmill that they were making, and they weren't covering the tread at the very end of the tread, and it could pull small children who were playing next to the Peloton underneath the Peloton. No major injuries, but the Consumer Product Safety Commission made a big deal about it. And so clearly this device has pinch points on it. Do you have anything in your documentation addressing that safety issue?
It does say if a child were to use it, which wouldn't be super likely, but if a child would need to use it, that to consult your physician and to have an adult on hand. But yeah, to monitor them. But if you're asking if there's like I don't know, like a disclaimer about injury, that hasn't been established.
Okay, so I think it's worth noting in your documentation that there are serious pinch points on this, because when that thing slams over to one side, even if somebody is not on it, that could hurt,
Right.
Yes, yeah.
right?
Yes.
Okay, next safety question. The base, I understand you have restrictions on the base size, but the base is relatively small in terms of width. Did you do any calculations about where if the center of gravity, if somebody loses his balance and is falling to one side or the other, but holding onto those rails, did you do anything to compute where that center of gravity was going to be relative to the center of rotation, which would be the edge on the side that they were leaning, to see if this thing could get pulled over accidentally?
To get pulled over off of the ground if they maintain hold of the handle while they're falling.
Yeah.
Okay. So if that were to happen, we haven't done any calculations necessarily for that, just because of how hard it is to kind of gauge the weight and security of the board on it, and just the problems that we've been having the past couple of days, limiting the amount of testing that we could do. However, the way that the handles are screwed in it's screwed into the bottom plate so that it's all kind of one unit at the bottom. So if a user were to fall, they would only be falling about 6 inches or so at max, and so they wouldn't be able to take it that far just because of how wide the board is.
Okay, so humor me.
Okay.
Let's get your video looking at the device.
All right. We can probably just do the laptop camera.
Okay. Now, here's what I want you to do. Let me pin that where I can see it good. All right. Now, what I would like you to do is I would like you to lean as far to your right as you can while still holding onto the bar. Now, your upper body too. How far can you push your upper body out? Okay, you're safe. That's all I wanted to know. We're good. Okay. See, that was easy.
Yes, sir.
Okay, the next thing I would like you guys to do, you've been talking about this Velostat,
Yes.
and that's great, but I'm not sure that I've gotten an explanation of how electronically, how does the Velostat based on pressure give you a different voltage?
So I kind of tried to go over this in one of my software flowcharts, but essentially it is a conductive material that forms a barrier between the rows and the columns, between two copper wire strips going in the grid. So the more pressure that you place on it, the more resistance there is, and the higher ADC value you get. And so the way that it's like looping through, reading one square at a time, it populates the ADC value by how much pressure the user is putting in that particular spot, and forming that into the pressure sensing grid.
So let me rephrase what I think I heard. Tell me if I'm correct. What I think I heard is that the Velostat is actually conductive. It is a conductive sheet,
Yes.
but it's a relatively high impedance. And as you put pressure in a particular area, that the conductance increases or the resistance decreases, whichever way you'd like to say it. Is that what you're describing?
That's
Yes.
correct. Yeah, as pressure gets applied
Okay,
to the mat, the resistance should decrease, and we can see that change on our side.
okay. So I haven't seen in any of your presentations anything that shows me really how I'm going to build this. Yeah, you've got a 3D model of the thing, but do you have any place where you have dimensions, instructions for making the Velostat mats with dimensions? Do you have anything in your theory of operation about how it is that we calculated the values for the Velostat pull-ups? Tell me what you got.
We haven't written down anywhere how the user who we assumed would be purchasing the product already built would make it themselves. But we can provide that documentation for you.
So this isn't about the user. Dr. Kim wants to build a second one.
Okay. Yes.
She told me that she wants to build 15 of these. Do you have instructions that somebody can build 15 of these?
Not currently.
No.
It wouldn't be step-by-step instruction, but like you mentioned with dimensions, the dimensions on the 3D model are accurate. But we would need to add additional information if you wanted to completely build from ground up.
So do you have a complete bill of materials for everything, including all the wood pieces, screws, pipes, any of that?
The wood and pipes and such. Nate's dad has a shop back at home. So most of the pieces that we gathered, most of the physical pieces, like the wood and the pipes and everything, Nate's dad had scrap. So we just sourced all that together and built it up. But we do have dimensions on the parts themselves. I guess same thing with the screws and the nuts and everything. We had them just laying around, but we didn't have. We haven't exactly written it down.
Okay, so here's the thing. You've been working on an engineering product that is supposed to create a working prototype. If I can't reproduce that working prototype, you have failed.
Yes, sir. We can.
So I need to make sure that you understand that I'm going to be triple checking your documentation for mechanical documentation and the ability to mechanically put this puppy together. Because if that's not there, you can't get a passing grade on that.
Okay.
Okay. Next question that I have. So on your software, you're demonstrating on a Mac. Does your software run on Macs and PCs or only on Macs?
So the desktop GUI does run on both Mac and PC or Windows
Okay.
system. The only change that you'd need to make is the serial port that the Windows product is receiving Bluetooth on it, which I believe is just COM6.
Uh-huh.
For it to run on my laptop, it had to be changed.
Okay. So I have one last question, or one last pair of questions that I'm going to ask each of you to respond to individually. Question number one is, what is the biggest takeaway for you, the best learning experience that you had out of this 419, 420 series of courses? And the second one is to let me know if you have any suggestions on how we might improve this course.
Okay, I'll start. Okay, so my biggest takeaway, I think, can be two things, both related to the project in different ways. So one of which being how to time manage and actually do a project that was long term. Of course, we've done labs and stuff in our major and things like that, but this was definitely bigger scale and more, I guess, realistic and applicable to a real world situation. So I think that that was most beneficial into migrating from a college project to actually having a job, and being able to be on a team and work with other people. So like I said, we've done this in the past in different school projects, but this was a little bit bigger scale, and I think that that was really beneficial for us to learn about. And then obviously on the other side of things, just being able to apply knowledge from courses that we've already taken and put that into action for the project. But also knowing how to research. I think this was a different level of research that probably any of us have ever done. So being able to do that on a bigger scale was a big takeaway for myself. And then what was the second question?
What would you improve?
Oh, I think the layout of the course was very, like I don't really have any big complaints. I think the TAP meetings every week was very helpful because you gave good, instructive, it was either instructive criticism or just here's something to improve, that kind of thing. And it was done so in a way that was, not necessarily like making us feel like we were failing or anything, but it was definitely, constructive, and we took it to mind and, addressed any sort of questions or problems that we had. So I think, I guess I don't really have a complaint about that. It's more of actually a compliment of, the TAP meetings, I think, kept us on schedule and made sure we were checking in on each other and that kind of thing. So I definitely liked having those meetings for, progress updates.
Okay, thank you.
As far as the biggest takeaway that I took away from this course was basically how freeing it was to have a project that had no one set way of being completed. Unlike some of the other computer science courses that I've had that you can only code something one way. I think it's quite often that a lot of 420 teams use LabVIEW or something for data processing or visualization, and being able to kind of be different than that and change to something that I was more familiar with and kind of rethink how I want things to be seen or done in code, and not having one set way of doing things was just kind of fun for me to sit around and think about all day, and then try new things, fail some places and then learn from it and succeed the second time or the third time or the 50th time. One of the things that I think could be improved, and I think that this is just because we've had an abnormal experience of not being fully in person, maybe having like a little bit of in person but not completely, is just not having access to one lab that we can go work on it. Like a lot of the study rooms in Zach where we would have liked to do research or planning or some meetings don't have 4-person limits in the rooms, it's less. And so if we try to get together anywhere outside of our own, homes or apartments, then we kind of got kicked out or something. And obviously the PIC is traditionally where most 420 teams do a majority of their work. Well, we found that we had to do it here. So if we did run into like a hardware issue or we wanted a fresh set of eyes, then there wasn't another team there that we could say like, hey, like, what do y'all think we should do? So, and I think that did benefit our team so that we could sit and struggle a little bit, and that kind of helped us get through some problems. But as a whole, like it would have been nice too to have that experience with other teams that are working on different projects to see how they think. And it would have been interesting to see how our design had changed had we had that experience.
Okay.
My biggest takeaway from working on this project was the sheer amount of work that goes into all of this. So like with 419, what everything that we were doing was kind of theoretical, some testing and everything, but we had to hit this semester running, and we were already behind when we started. We had to work exorbitant amounts of hours to catch up to a good place and then maintain that level of work throughout. So I feel like it might have been just time management issues on our end, where we just didn't plan it out perfectly. So it was interesting to see how that, how time management plays a big part in all of this. My biggest, I would say the one thing that I would recommend was with 419, it was set up as a theoretical course, in my opinion. I would have liked to, like mid-semester of 419, have Dr. Crosby or anyone just say, hey, you should be starting to order some of your preliminary parts and start testing and everything. Because we tried to do that, but with some of our testing, we originally had a magnet design, which failed, but it fell towards the end of the semester, end of the 419 semester. So we had to, try to find different ways to implement it. So it was just, I think starting testing in the middle of 419 would have really helped to keep us on track without having to worry about catching up.
Okay.
For me, probably the biggest takeaway that I had is just how fun it can be, like the frustrations but also like the success of designing and building these things and how it just all kind of plays out. And then things that I might improve would probably be, with 419, I wish it had prepared us a little bit more. It felt like we were never encouraged to do that, or kind of like testing. And I wish that could have been included in there, because I think that would have saved us some time early in this semester. But then with 420, I thought the TAP meetings were great, though sometimes it did feel like they had to be ended because of just time constraint. And so, yeah, being able to spend more time on those would have been nice.
All righty. Well, I think you guys have done a good job. You still got some additional documentation you need to get together for Dr. Kim, but and some additional work on the prototype, so that she will be pleased with that ultimately. And the way that I'm going to do this so that we get the grades in on time, I will go ahead and enter in a grade that you would get for your final demonstration, as if you did not complete the stuff that you are going to complete for Dr. Kim. When you do complete that to her satisfaction, she'll send me an email and I will update that grade. So I want to say a special thank you to Dr. Kim. She has sponsored more and been faculty advisor for more projects than anyone else in our department. And she is not using that as an excuse to shortchange you guys on time. She really does give a lot to making sure that you guys are a success, and that you learn how engineering is done in the real world. And I really appreciate everything that Dr. Kim does, not just for our department, but also for you guys individually. And I hope you guys appreciate what a great asset she is.
Absolutely.
Yes, sir.
Thank you so much, Dr. Kim.
I think I can speak for myself and the rest of the team in saying that I'm incredibly impressed with all that she's capable of handling. I don't know how because I know like some people in her 359 class, and they'd have an exam that week, but then she's also doing Capstone. So you're able to manage a lot, and I'm very impressed. So thank you for putting time into our project, and everybody else as well.
Well, and thank you for the team as well. Like I was kind of had the high expectation, and I pressed them quite the multiple times, but they were actually made it work. And then well, this presentation is more than what I expected. So I'm very happy, and the handles or things is I just told them like I can help you this and that, but I actually didn't made it out, but they just had the plan as a backup, like plan B. Like I'm not really supporting that, but they made it out really well. So I'm very happy for this team particularly, and we had the good preliminary data with this rehab study. So we really wanted to have a more right version of it. So I'm really thrilled we have a prototype, and well, we had the some material from a shop from the team members' parents, and the things actually probably help to save some money as well. But like it's considering it's a low cost, and never had this kind of low cost, but has the feature like this. So you have a better low berry. So I'll shut up really quickly. But anyway, yeah. So I'm very hoping it can be a good extension for the future study, and I hope like some of you are continuing as the master program can extend the study from here, and also a good publication out of it. Okay. All right. And thank you, Professor Willie, and your support
very
and
welcome.
your TED meeting and your all the advice actually helped a lot for the team.
You're very welcome. Well, gang, we will, with that, we will end this. Make sure that you get your, so final steps. Number one, you need to obviously take care of Dr. Kim. Number two, you need to finish your final documentation. Email me when that is ready and posted on the drive that you've shared with me, so that I know when it's time to go grade that. And don't forget to turn in your peer reviews if you have not yet, because I can't turn in grades until those get turned in. Make sure any equipment that you borrowed is returned to whoever you borrowed it from, and that Dr. Kim gets everything else.
Okay.
All right?
Thank you so
And
much.
two thumb drive, one for me and one for Roseanne.
Yes.
Mhm.
All right.
All right.
Thank you very much.
Thank you.
Okay. Enjoy your week.
You too.
Bye.